Hello everyone, this is Rudree Pathak from Department of Pharmaceutical Technology, LG Institute of Pharmacy, Ahmedabad. Welcome to the online MOOC lecture series, an initiative taken by LG Institute of Pharmacy, a part of LG Group of Institutes. In today's session, we are going to talk about our third basic state of matter, and that is the gaseous state. Now, I'm sure you must have learned about this in your school curriculum in 11th and 12th standard physics or maybe even in chemistry. So let us first understand what are we going to talk about in today's online lecture. So basically, a gaseous state is characterized by certain properties. We have listed a few over here in the presentation right now. Generally, gases are known for their random arrangement of atoms, ions, and molecules. The pressure which they exert in a closed system is known as vapor pressure, and gaseous state is known as a compressible state of matter. How do we define a gaseous state, or what are the laws which actually affect their overall properties? So basically there are two different kinds of laws which affects gaseous state. That is ideal laws and real laws. We are going to talk about ideal gas laws first. Now there are certain assumptions based on which ideal gas laws are actually defined or derived basically. Now it is based on an ideal situation where no intermolecular forces of interactions are going to happen, and even if molecules are going to collide, then the collisions would be perfectly elastic without any loss or transfer of energies between the gaseous moieties. So based on this assumption, ideal gas laws actually come in the picture. Now, there are three scientists based on whose theories actually gaseous laws, ideal gaseous laws, are defined or derived. So, the first scientist was based on Boyle's theory. Now, according to Boyle's law, we have a relationship between volume occupied by a gaseous system and the pressure at which it is actually measured. So, we have our first equation as PV equal to K. So it states that pressure multiplied by volume is equal to a constant parameter. Second is we have combined the postulates of Gay-Lussac and Charles, which gives us a relationship between volume occupied by gas at a given temperature. And that theory gives us our second equation, which is equal to volume occupied by gas is equal to a constant multiplied by the temperature at which the measurement was actually done. Now, if we combine these two laws, that is law number 1 and 2, we have our third equation, which is shown over here in the presentation right now. That is P1 V1 upon T1 is equal to P2 V2 divided by T2. Now, this is based on two situations which we have compared for the given gaseous system. If we straight away derive a simple equation, then we can have our ideal equation as PV is equal to nRT, where N is the number of molecules or number of moles of gaseous system which are under observation or which is being tested. Now, this ideal equation was based on certain assumptions which we discussed in our previous slide, that there won't be any kind of intermolecular forces of interaction, and even if the interaction is taking place, there won't be any exchange of energies between the moieties. But real gases do deviate from this ideal equation and they do not obey this ideal gas equation, and these are known as real gases. Now, real gases show deviation from the ideal behavior at low temperature and high pressure systems. And that is why there is a need to derive a separate equation for such kind of behavior. Also, Van der Waals equation was based on the deviation from ideal gases, which is ultimately based on certain assumptions from kinetic molecular theory. Now, what that kinetic molecular theory actually says that intermolecular forces of attraction do not exist. There are no attractive or repulsive forces between the molecules of a gas. Also, there was one another assumption, that is the volume occupied by the gaseous system is much less than the volume which is occupied by the entire container in which it is placed. So real gases actually deviates from this postulates of kinetic molecular theory, and we have another or separate equation for that, which is shown over here in the slide. So this particular equation is based on real situation or deviations which gaseous system actually shows at low temperature and high pressures. So this is actually utilized for calculation of certain parameters when the system deviates from ideal postulates of kinetic molecular theory. Thank you so much for your patient hearing. In today's session, we talked about our third state of matter, that is gaseous state. There are two separate theories which actually define the gaseous behavior. First is ideal situation, and that is based on the assumptions given by Gay-Lussac's law, Charles' law, and Boyle's law. We also talked about the real situation where the gaseous system deviates from the ideal parameters or postulates and show some different behavioral pattern. Thank you so much for your patient hearing. Do like, share and subscribe our YouTube channel Pharma Ignite for further updates.